All right, welcome back, everyone. So let's continue. By the way, is the microphone, is this working with that one? Yeah, good, perfect. All right, so we learned a lot about vectors, and yeah, a lot of this was just very simple definitions, a lot of terms. But of course, it is important to be familiar with those terms because those are the very basic building blocks that all what we are going to do now will be building on. So we learned about vectors, different kind of vectors, different characteristics of them, and also very simple arithmetic. So now let's look into a little more advanced arithmetics, still not really that difficult, but a little more advanced than the simple scalar multiplication or scalar product, or no, scalar multiplication and addition. And the first one is, of course, the scalar product. Or dot product, or inner product, as it's often called. So we talked about addition of vectors and subtraction of vectors. So of course, the natural question is, of course, is there also something like a multiplication of vectors? And short answer is yes, there is something like a multiplication of vectors. In fact, there is not just one multiplications, but there are different types of multiplication. Because vectors are not just single numbers, but they are collections of numbers, so we can define multiplications in different ways. And there are two major ways in which multiplication with two vectors is defined. So the multiplication that we had so far was the multiplication of a single value with a vector, the scalar multiplication, where we just take one scalar value and multiply it to all the coordinates of a vector. But the scalar product now is a product of two vector values, but it's often called the scalar product because the outcome of it is a single value, a scalar value. And it is defined as in the following way: we take each coordinates pairwise again, multiply them with each other like we do for the addition, but then we do not create a vector, but we create a scalar value by taking the sum of all these individual products. So V1 times V2, V1 times W1 plus V2 times W2, and so on, depending on how many values, how many coordinates we have in our dimension. And then we get, of course, a single value, a scalar value. And that's why it's called a scalar product or dot product, because we denote it usually with a dot in the middle. Also, sometimes it's called inner product. And of course, this is something, it's basically just a definition, but the definition is done because this kind of value that we get has certain characteristics which are quite important and quite useful, especially in computer graphics. And one of the most useful characteristics is the relation between the scalar product, the length of the vectors, and the angle between those vectors, or more concretely, the cosine of the angle between those two vectors. So I assume you all know or have seen the cosine function before. You probably don't remember it, but I'm pretty sure you have seen it once from the school. The cosine function, which is why I plotted it here again, the cosine function is the blue one, which starts at 1, then goes down to, depending on if you do it with angles, you're talking about degrees. If you do it here, it's based on the pi, but if you do it with angles, with 90 degrees, you're at 0, then you go down to -1, then you're by 270 degrees, you're again at 0, and then by 360 degrees, you are again by 1, and then it continues periodically. And this cosine function of the angle between the vectors has this interesting relation between the scalar product that if we take the scalar product, the result of the scalar product, divide it through the product of the lengths of these individual vectors, then we get the cosine of the angle. Or more conveniently, more useful, written actually the other way, that the vector, the scalar product, can be calculated in this way based on the length and the cosine. And in fact, that is sometimes in some sources even used as a definition of the scalar product. And then they show that this relation here is actually the same, or that this is actually a way to easily calculate it. I personally prefer this definition that I had here because it fits also better into the arithmetic definition of addition and so on. and use this more as a characteristic, but they are interchangeably. You can show that if that is fulfilled, then also the other must be fulfilled, and the other way around, which is why both of them are perfect definitions of this dot product. Now, from this definition or characteristic, you have it's very useful because you can see already certain characteristics depending on the value. So, for example, if this dot product is 0, then we know that the cosine, because if the dot product is 0 and none of them is a null vector, which means none of them has the length 0, then we know that because we have a product on the right side, the cosine must be 0, which means if you look at the function, the angle between the two vectors must be either 90 degrees or 270 degrees. So we know they are orthogonal to each other. Or the other way around, if we want to know if two vectors are orthogonal to each other, we can just calculate the cross product, the dot product with this formula, and then we know they are in a right angle without even calculating the angle. Likewise, if we have unit vectors, then we know, of course, for unit vectors, the length is 1, so this part of the product is 1. So we know if the scalar product is 1, the cosine must be either 0 or 180 degrees. So it means they are pointing in the same direction or in exactly the opposite direction, based again on the cosine function, because the cosine function has a maximum of 1 and minus 1. And if we see that if the length is 0, then of course we have this maximum reached at 1. Good. So this is so it basically is a very easy way to, for example, calculate vectors. So every time you have something, you have two vectors, and you are dealing with the angle between these two vectors, the dot product very often comes in very handy, especially when you're dealing with rectangular vectors that are perpendicular to each other. There are, of course, a lot of other characteristics that this dot product has that in certain situations are also very helpful. I have just written down one here, which, and the reason I have chosen that is, first of all, just to illustrate there are other characteristics that are interesting, and secondly, because we will use that later in a proof, so I can refer back to it and I don't have to show it again. And also it kind of repeats the trigonomic relationship that we also have with the cosine, because the cosine is not only a trigonometric function, but it is also gives a relationship in a triangle, and it is defined in a triangle. If you have a triangle with the right angle, then the cosine is defined as the length of this side divided by the length of this side, which is in this case the length of the vector v, and in this case, oh no, that was the sign that I said. That's wrong. This is the cosine. This length, I denoted here by p, is the length that we get when we project this vector onto this other vector here, which might not seem interesting for you now, but we will see later a situation where we have that, and then I will refer back to this and say, yeah, you remember, you know how to calculate that length, namely by using the cosine. The cosine is this length p divided by the length of this vector. So if we put the cosine in here, we can actually calculate the length p without even calculating the angle phi, which I forgot to write down, theta, the angle theta, which I forgot to write down here. So, good. So, wait, that's the wrong direction. Yeah, so we see we have all kinds of useful characteristics of this scalar product, which is why we use it very often in graphics. But of course, it is just a multiplication of two vectors that leads to a single value. So we can also ask ourselves, is there a multiplication when we multiply two vectors that leads us to a vector, in the same way as if we add two vectors, we also get a result as a vector? And the answer is, of course, there is one, and it's called the cross product. Now, the definition of the cross product looks not really straightforward at all. It looks actually quite weird. We just take two coordinates from the vectors, multiply them, and subtract the product of two other coordinates. And it's something that, yeah, there is not really an intuitive understanding behind it. The reason why we have this weird definition here is basically that the resulting vector has something characteristics that are very, very important, very, very useful when we're doing graphics, and we will see that very shortly. So, but before that, yeah, let's also quickly look, note there is also a trigonometric relation between our characteristic with the cross product, which is the length of the cross product is the same as the product of the length of the individual vectors times the sine of the angle theta between the vectors. But be careful here. Here we have the length of the cross product because we are dealing with scalar values here. So this is not like in the scalar product case an alternative definition of it. This is really just a characteristic of the cross product, and a characteristic that will come in quite handy, as you will see later. Good, but now for the most important characteristic of the cross product, which justifies why we have this weird looking definition of this multiplication of these two vectors, the most important characteristic of the cross product is that the resulting vector is perpendicular or orthogonal to both of the original vectors that were used to create this cross product. The vector, for example, here I call them v and w. Forgot to write it down here. If this is the vector v and this is the vector w, then the cross product of these two vectors is a vector that has a right angle to both of these vectors. And we will see later during the course of this lecture of this course that we will need these kind of vectors very, very often, so you will do a lot of cross product calculations. Now, the question is, of course, how do we see that, or how can we prove that? We probably don't see it. If you just look at the definition, I'm pretty sure very few people here would say, yeah, I immediately see that this is in a right angle to the original vectors. But we see it very easily if we would do a mathematical proof of it. And I already told you in the first part, there were a lot of situations where I said, or a couple of situations where I said, yeah, we could do an arithmetical proof about it, and you should do this in the tutorials. But you probably don't know how to do it, and that's why I have this example here, because this is very simple actually. We can prove this by remembering that the scalar product is 0 when the two vectors have a right angle. So what we do is, when we want to prove the claim that the cross product is perpendicular to these original vectors, so we just take the scalar product of the cross product with each of the original vectors, and if that cross product is 0 for any kind of random vector that we can choose, then we have proven that for any random vectors v and w that we choose, that their cross product is perpendicular to them. And if we do that for any kind of random vector, we just basically write down it with this generic form of coordinates that we can fill with all kinds of values, and then we see this is the vector v. This is the cross product for the vector v cross w. You can see that from the definition if you look up. So be careful, there are commas here. So this is not a scalar value, but this is a vector, like here as well. And then you see if you do the scalar product, like we had in the definition, where we take the v1 times this value plus then v1 times the other value and so on, then you see you get these values here. Now we know that these are all scalar products of scalar values here, and we know that scalar multiplication is commutative, which means we don't have to look at the order. The order doesn't matter in which we multiply the individual values. That means v1, v2, v3 is the same as v2, v1, v3. And since one is positive, the other is negative, that is 0. Here again, we have the same situation. Minus plus the same thing leads to 0, here 0. So indeed, the scalar product of these two vectors is 0. So the two vectors must be perpendicular to each other. We have proven that. Then we have to prove the second case, which is just the writing down. So it's pretty much the very same thing. And then we have proven the right side. And then we have proven that this vector is indeed perpendicular to these other two vectors. So it is actually quite simple. It's quite simple to calculate if you remember the definition. It's also quite simple to prove if you know how to prove it. Now, there is one thing that is a little open, vague here. Any idea? If you have one vector and you want to have a perpendicular vector to that one vector in 3D and you want to have a perpendicular vector to that in 3D, there is an infinite number of vectors that you have, because basically every vector in a plane that is perpendicular to that vector is of course perpendicular to it. Now if you have two vectors, then of course there is only one solution, as I showed here, but that's not true. There are two solutions. It can also point in the other direction, and that is also perpendicular to these two vectors. So the question is, which one do we get when we do the scalar product? And the answer is, let's first look at the case where we have unit vectors and look at this characteristic again. This is where this characteristic comes in quite handy, because if we have unit vectors, then we see that the length is again a unit vector. Is again a unit vector, but again, of course, we don't know which direction, but we also see here this is positive and this is negative. So if we write it down like you did here with the coordinates the other way around, you will see and you can prove that this is actually the case, that depending on in which order you multiply them, you will get either the vector pointing up or the vector pointing down, which translates then to 90 degrees or 270 degrees, or the plus and the minus here. Good, so we see a cross product is not commutative, like subtraction, it just leads to the vector in the opposite direction. Good, now a few more characteristics, and I just included that here to give you an example for all these exercises that you have to do in the tutorials. So this is actually not that much about telling you teaching you about these characteristics, because if you think about it and if you think about what we just said, it's pretty obvious what the answers to these are. The thing that I often observe is that there are a lot of people here, especially the people who have no mathematical background, when they hear, oh, I have to make a mathematical proof, that's going to be difficult. I don't understand that. But that's nonsense, because these proofs that we do here are so simple if you know how to do them. And that's why I have these examples here, although they really are quite simple. So one question is, what is the cross product of a vector with itself? And the other question is, what is the cross product of two vectors that are parallel? And we can make a formal proof by it in the same way as I've proven that these vectors are perpendicular to each other, by just taking the individual coordinates and then, the answer in both cases is the null vector, which, and that is the thing that we want to prove, and we prove that by just taking the general case, taking the coordinates, writing it down, doing the simple arithmetic transformations, and then you see it's the result, for example, for the first coordinate is 0, because if you look at the definition, and you, where is it? Here it is. And you just write it down with vector v is then not, vector w is not vector w, but vector v again, then you get here v2, v3 minus v3, v2, which is obviously 0. And for the second and third coordinate the same, and then you get the null vector. And the same is here. If you have a parallel vector, that means that you can write the second vector as a scalar multiple of the first one. So we have some value lambda. We don't need to know the value lambda, because we also want to prove the general case. So we just write it down, and you see here again, you get a very simple equation that equals 0. So it's basically just thinking about how do I formalize it, how do I represent it, and then just writing it down, doing some simple arithmetics that actually show exactly what you are looking for. In this situation, there would have actually been a second way to prove it very easily and very simple, which is remembering this characteristic here, because if you remember that, and then you know, okay, the sine of theta is 0, for these two angles here, for the angle 0 and for the angle 180 degree, and then you know, of course, if they are parallel, they're pointing in the same direction, so the angle must either be or in the same direction or in the opposite direction, so the angle must be 0 or 180 degrees. If they are identical and the angle is obviously 0, so this length must also be 0, and we defined a vector, the null vector, as the vector with the length 0. So you see here, this is very simple, but the reason I'm telling you this is that I've often observed that people are then sitting in a tutorial and they see this and they're like, yeah, I have no clue how to do it and how to approach this. But this is what I also want to highlight to you, that because for me also as a student at the beginning when I started with these math classes, it always happened that I was sitting there and I was like, okay, I understand each single step that he does here on the blackboard, but if I sit in it myself and then I have to do a proof myself, I don't really know what to do. I don't know what to start. So this is also why it's important. Of course, try to understand each of the single steps I'm doing here when I'm doing a proof here, but also try to understand why am I doing this? What is the concept? What is the approach behind it? Because very, very often this approach is very, very simple, and very often I see, especially then in the exams, that people have no clue how to do that and give away a lot of points, a lot of credits, just wasted, although it is very, very simple. Good. I hope it's not too simple. All right, so much about vector arithmetics, and now we want to we have at least a basic framework in place to talk about something that is hopefully then a little more interesting, which leads then more to the computer graphics, which is then really describing certain objects with it. Of course, in this course, like I said, we're not doing full 3D modeling. We're just describing some very simple geometric shapes. So, for example, today we'll talk about lines and circles in 2D, and we will use this vector framework, this vector concept that we just introduced to do that. And there are different ways, of course, to describe these objects in 2D, and later then next week in 3D. And two of the most important ones that are often used in graphics are the so-called implicit and the parametric representation. So let's start with the implicit representation. So if we're defining it on an abstract level, we say a 2D shape. We call it often a curve, an implicit curve in 2D. So a curve is intuitively basically every kind of shape that you get when you put the pen down, draw something, and release it. So everything between this putting it down, drawing, and releasing is on a paper that can be considered as a curve. And of course, we want to mathematically describe that. And if we look at this at the example at the top, you see this red roundish shape here, and one of the ways to describe it mathematically is by a function that equals 0, which sounds a little strange at the beginning, but if you think about what it is, if we have a function from two values to a third value, what we basically have is we have a plane, an xy plane, and then we map we assign one value to each coordinate in this two-dimensional space. And then we say if this value is 0, then we draw a curve, and if it is not 0, we do not draw a curve. So if you think about it in 3D, the intuitive image about this is you have a landscape, and your xy plane is then the z level, and the coastline is then your curve. And that might sound a little weird now, but you will see later why or in which situation this kind of representation is actually very, very useful and much more suitable than other representations that we see later that might seem more intuitive now. So I hope it gets more intuitive when we look at the concrete example, which is a circle, because of course this is the abstract idea behind it, but the interesting or the difficult question is, of course, how do we find a function that describes the shape that we actually want to draw? And a very simple shape, or one of the most simple shapes, is of course a circle. How do we define now a function that draws a circle, or a function that fulfills this condition that the function values are 0 when the points x, y are on the surface of this circle? And I'm claiming now that this equation, x to the power of 2 plus y to the power of 2 minus r to the power of 2 equals 0, defines a circle. It fulfills this condition that if x and y are on the circle, then this equation is 0. R denotes, of course, the radius of the circle. And we can see that quite easily if we remember what we did in the first part with the vectors, when we talked about the length of the vector. So if we look at the image, if we represent any random point on the circle surface with a vector from I'm not sure if I said that, a circle around the origin. That's the first thing we're looking into, a circle around the origin. Then we can represent each point on a circle surface by a vector pointing from the origin to this point on the surface. And if we do that, then of course the length of the vector must be, of course, the radius, because if it's larger than the radius, it doesn't point, it points beyond the surface. If it's smaller, it's still inside of the surface of the circle. So it must be the length of the vector must be the length of the radius. Now, if you write down the definition of the length of the vector and then do transformations by bringing it to the power of 2 and then bring everything to one side, you get exactly this condition here. So this is really shows that if this condition is fulfilled, then the point must be really on the surface of this circle. Alternatively, you could have used, again, the Pythagoras, which we also used in relation to the length of the vectors, which, of course, is only defined for triangles. But if you're going here, of course, then you have negative values here. But because we have this to the power of 2, it doesn't really matter. So you can also use the Pythagoras here. And then you can also describe it by that and come up with the same equation here. Now, if we want to describe, of course, it would be very boring graphics if we can make circles only around the center of only around our origin. But we want to create circles at random points in our 2D space. So, at point, for example, that we describe by a vector c to the center of the circle. And now I claim that if we do that, then we have to subtract these two values here. That might seem a little strange now. Why am I subtracting it when I'm actually going from here to that position? But it is actually quite intuitive to understand if you look at it from the geometric interpretation. If you think about, you have this point here, and you want to verify, is this point on the surface of the circle or not? And if it is, then it should fulfill this equation and be 0. And here, we already specified that equation. If it is on the surface of this circle, then this equation verifies it. If it is 0, then it is on the surface of this circle. Now, if we are here, this vector here is basically this vector here when we add this c vector to it. Or we can say if we go to this point here is on the surface of this circle, exactly if this point here is on the surface of this circle, which is basically the whole circle shifted towards the origin. And that's where this minus comes from. That's why we have here to subtract the c values, the center coordinates from the x and the y value to verify if the point is really on the origin here. And I think this is also one of the details are also in the tutorials, in the exercise sheets. Good. So you see we can represent this equation for a circle now, and later we will see examples why it makes sense to represent a circle this way, although it might seem a little strange at first. We can also do it there is also, of course, an implicit representation for lines. And for that, we will, to define that, we will start with what I think most of you should know, which is the slope-intercept form, which I think is the most popular specification of a line. That's what is usually taught in high school, which is a line is defined by its intersection with the y-axis. So if this is our x-axis, our first base vector, and this is our second base vector, our y-axis, then we have the intersection with the y-axis is at the distance c. And then we go to a slope a. Why did I write m here when it's a? That doesn't make sense. A is the slope, which is defined by basically how much we have to go to, depending on how far we go to the right, it specifies how far we have to go up. So if we take 2 points here, x1, x2, and x1, y1, and y2, then we take the difference, which is usually denoted by delta, divided by each other, and then we get the slope of this line. And then for each point here on the x-axis, if we multiply it with that slope, we know how far we have to go up, and then we add the c value, because then we're not going only up, but we're also moving here, the line here. So this is the slope-intercept form, and as I said, I'm pretty sure most of you know that and are already bored now. And you will probably also be bored about the implicit representation, because this is, of course, very simple. We just take this and transform it and bring everything to one side, and then we have an equation that equals 0. So we can use that again to verify if a point xy is on the line, and it is exactly on the line if it fulfills this equation, if we put the xy values in there and it equals 0. Now be careful here, because I use the slope-intercept form I ended up with this equation here, and this is often very confusing because of course the official representation is something like that, because the point is, because we have something equals 0, we can multiply that with any constant value, and that will still be fulfilled because multiplying constant value times 0 leaves 0, so it only changes these factors in before, which are also constant values. And that way we can, for example, use that and create this equation here by dividing here by 1, or multiplying with 1 divided by b, or we can make it that the x has a 1 in front of it. Depending on how we want to calculate with it, this comes in then quite handy, but that's also why sometimes people are confused why I have these two different notations here. Good. Now now this is, like I said, we used this slope-intercept form to come up with the equation, but of course we introduced this whole vector concept first because this is very useful to describe these geometric shapes in graphics. So of course we are also interested in describing these implicit equations with a vector form. And if you remember how the scalar product was defined, you see that this definition here is actually nothing else but a scalar product of a vector p, which has our variables x and y, with a vector, I called it n, with the factors, the coefficients minus a and 1. Because if you put those into the scalar product, you will see that you will get exactly this equation here. So if this equation equals 0, it's exactly the same as if this equation equals 0. Now, of course, I said we want to describe it in vectors because we do everything in vectors in graphics, but especially in this case, this vector is also very, very useful, and that's also one of the major reasons why the implicit equation or the implicit representation of lines is so important in graphics, because this vector has a very unique characteristic. It is namely a normal vector to the line. And this is also something you can prove. Yeah, later. We'll prove it later. Okay, so for now just accept it. It's a normal vector to the line. But of course we do not only have lines going through the origin, but also lines that are at any space in our at any position in our 3D space. And now if we want to do that, we have to try to extend our equation in this way, which looks quite similar to the circle case, where we also subtracted the center of the circle. Now here, of course, we don't have a center of a line, but we subtract a point P0, which is on the line, which can be any point. For example, it can be this point here. And the reason why we subtract it can be illustrated in the same way as we did it with the circle. If you think about, if this is the equation for a line through the origin, then of course we know that a point that is here, or a point must be on the line here, if of course we take this point and subtract this vector p from it, and it is on the line going through the origin, then it must of course also be here. So if we take p, subtract p from it, or this value here, subtract p0 from it, then we come to this line, and if this line is on the origin, then we have this equation here, then of course it is fulfilled, and then we know the point is on the line. And this is so this kind of explains how we can come up with this equation here. Of course, now I have drawn this vector here because it draws nicely just to shift the line down, but since it's a line and not a circle with a center, but it extends indefinitely to the left and to the right, we could have chosen a point, any point on the line. So for example, if we choose, let me draw it here so I don't confuse you too much or screw up the drawing. If we choose this vector, then of course every other value moves here. So instead of just shifting the line straight down, we just shift it to the side, but because it extends indefinitely to the left and to the right, there is no difference here. So we can really use any point here. Good. Now, I already said that, of course, the interesting thing here, and this is a major advantage of this implicit representation, is that based on the definition of the equation, if we have it, we already have a normal vector to that line, and we will see later that normal vectors are very important. I think I already mentioned it shortly last time that for light reflection it's very important, because light reflects usually at an angle that is the same as the angle of the incoming light with the normal vector on that surface. And that's why, of course, we very often need normal vectors if we want to do the light calculation. Now the question is, of course, I told you it's perpendicular, but of course you are scientists, you should be critical, so you should be wondering, is it really perpendicular? So you should be asking for a proof. And the proof is, again, actually quite simple arithmetic calculation if you understand, or if you get the initial idea about what you have to calculate to prove that. And the proof is, again, of course, like I said, if we have if we have perpendicular values, it is always, the scalar product is always something that comes in quite handy, because the scalar product is 0 if two vectors have a right angle to each other. So if we think about what does it say a vector is a normal vector to any random point on the line, it means that for any vector that is directly on the line, if we multiply it with that normal vector, the scalar product must be 0. So we can, if we represent any random vector on the line and then prove it for that vector, then we have proven that the vector is indeed perpendicular to the line. And we do that by taking just two random vectors on the line, building the difference of them, which is then a vector on the line, as you see here in the image, multiply that with the normal vector, do this simple arithmetic transformation that you see here, and then if you arrange the values cleverly, you see that one of them is f of p0, which must be 0 because p2, because p2 was chosen as a vector pointing to the line, so the equation must be 0 for the line, that must be fulfilled. The same is for the other point, that must also be 0, so the whole equation here becomes 0, which means that, of course, the scalar product is 0, which means that these two vectors are indeed perpendicular to each other. By the way, this is also another illustration of, I've drawn this normal vector, of course, here, because here you have this minus a and 1, to illustrate this, that it has a right angle to this vector p1 minus p2 here, but the vector itself, of course, is, if you don't have this reference point, is of course here. So again, be reminded that the vector is an abstract concept, and it only depends on in which context you use it, then at which position it really points to in a 3D space. Good, yeah. So like I said, normal vectors are very important, which is why we also have to extend this notion of normal vectors. I only introduced normal vectors with respect to other vectors. I said a vector is normal to another vector if it has a right angle with it. But of course, we're also interested in, for example, having normal vectors for a sphere, for example, because a sphere, we also want to calculate the light influences, so we need normal vectors for spheres also. So we extend this notion of a normal vector to a surface normal, not a vector to that is perpendicular to another vector, but that is perpendicular to a surface, by saying it is a normal vector if it is perpendicular to the tangent plane on that surface. So the tangent plane, for example, to a sphere is a plane that just touches the sphere in one point, and that point is then the point where you are calculating your normal vector. So the image should illustrate it quite well, although it's a 2D image and not a 3D sphere. Good. So let me see, should I continue here? Yeah, let's just do the lines. Good, so this is the one way to represent geometric shapes is this implicit equation, but I said there's this implicit representation, but there are also other ways, and one of them is the so-called parametric representation. And like I said, we have different representations of the very same thing, because depending on what we're using it for, a different representation might come in quite handy. Like I already said, if you have something with a light calculation or something where we need normal vectors, keeping lines as an implicit representation is very useful, because then we can immediately see the normal vector. But this implicit equation basically, I mean, the name implicit comes from because these values are implicitly encoded in this representation. They are not really, you cannot really directly calculate them, but you take the points and put it in the equation and you verify is the point on the screen in this equation or not. So for example, if you want to draw a line, if you have one pixel and you want to draw the next pixel, it's kind of pointless, of course, to take all the pixels from the screen and put them in the equation to just figure out which is the one pixel which are the pixels that I have to draw, because these are only the ones where this equation is 0. But what you want to have is, of course, an equation that gives you the possibility to calculate all those pixels. So you have one pixel and you want to calculate the next one when you draw the line. So it's like you're walking along the line, and then for each pixel you want to have the coordinates. And this is exactly where these parametric representations come in. The parametric representations also describe a curve, but they describe it based on a single parameter, or on a parameter that is one less than the dimension. So in 2D, 3D we'll handle next week, 2D we have 2 dimensions and we have one parameter that controls us, and if we increase that parameter we get all the points that are on this curve listed in a sequential way. Or you can also think about it like for the implicit, the intuitive interpretation of it was you have a landscape and then you cut it at sea level, which is then the plane 0, and then you get your curve. And the intuitive interpretation of a curve for the parametric way would be you're walking along the curve, and then each time step that you make is then the next value that it gives you. For example, if you have a line, it's basically walking along the line step by step, and for each point, for each next step, you get then the value. Good. So let's look at the example of a line, because that's of course the most easiest, and it's actually seems easier than the implicit definition of it. And I'm pretty sure, of course, some of you, if you had vector theory in school, have already seen it. The idea is you basically have one vector that points to the line, that gives you a starting point, and then you know, okay, this is one position in space where my line is, and then you need a direction where this line points in the space. So you need another vector that points to it, and you can use that, or can create that other vector by just taking a second point on the line. And I hope your geometric understanding is good enough that you would intuitively agree. If you have 2 points, then you can use these 2 points to define a line. And the mathematical representation of it as a parametric equation would, of course, be you go to one point and then you go to the next point, and that point can be described by the vector that is the difference between these 2 point vectors. And when we write it down, of course, we can have it here in vector notation, here by saying this vector on the line, or a point on the line, is defined by this vector P0 plus then this vector, and then we scale this vector by t. So remember, we had the scalar multiplication, which is a multiplication of a vector with a scalar value that basically just changes the length of the value, or if it is negative, it changes direction, the opposite direction. So by choosing all values t from R, all possible continuous values here, we can go and calculate each point here on the line in this direction. And of course, if t is smaller than 0, then also in the opposite direction. So that should be very intuitively clear and very simple to understand. And these are the 2 vectors that define the line, and that's why they often have a special name. They're usually called the support vector or the direction vector, depending on in which book or which source you look. You also find sometimes position or displacement vector. Good. Yeah. So we have basically now 3 representations of a line, and we will see examples later why these representations are useful, and which situation, which representation is more useful. And you hopefully also see it in the programming assignment. So it is also, of course, important to be able to transfer between those different representations. And this is actually one of the exercises in the tutorial, and it's actually also a good way for you to repeat this and to remember what we learned today, which is why it's also a good position to stop here today and close the lecture. There are a few more exercises on the tutorial, I think, that cover the stuff that I haven't talked about yet. So if you come to those, just skip them and do them then next week. Good. Any questions? No, then I wish you a happy Queen's Day, and we see each other on Thursday again. So Tuesday is holiday.